Good morning. Today we're going to talk about, or really continue talking about, a more conventional analysis of circuits, and we've been doing this sort of macroscopic view. This connects to readings on meters and circuit diagrams. And so we're going to be talking about conventional current instead of electron current. Remember, conventional current is amperes per second. Amperes, which is a coulomb per second, as opposed to the number of electrons per second. We'll still be talking about potential differences. We talked last time about capacitance, which is a measure of charge stored on a capacitor, and we're going to introduce the concept of resistance. We're still going to be using exactly the same strategy to analyze circuits, in that we'll be using loop rules, so a loop rule, I remind you, is the name in the context of circuits for the idea that the round-trip potential difference through any path has to be zero. And a node rule, the node rule really was just conservation of charge and definition of steady state, and it said that current into some location on a circuit, some node, had to be equal to the current out. And we expressed it in terms of electron current, but of course it works exactly the same for conventional current. So the conventional current into a node has to be equal to the conventional current out of a node. So there's really no new physics here. It's just the same ideas, but we're going to be using slightly different quantities to describe it. So so the first of these quantities is conductivity. And where does this come from? Well, remember that we had conventional current was the electron current, the number of electrons per second multiplied by the charge on an electron, or the number of mobile charges per second entering a section of conductor multiplied by the charge of this thing. And since electron current was the product of the density of mobile electrons, the number of mobile electrons per cubic meter, times the cross-sectional area of the conductor times the average drift speed, this must be another expression for conventional current. And we can write this, actually, since we know that the average drift speed is equal to the mobility times the magnitude of the net electric field at the location of the mobile charge, we can amplify this even more and write an expression for conventional current at some location, the absolute value of a charge. So we've got our fictitious positive charges again, times the mobile electron density, cross-sectional area of the conductor, the mobility of the electrons, how fast they go for a given electric field, and the electric field. Now in this expression, we have a whole bunch of stuff jumbled together. Some of these things have to do with the particular material. So what the mobile charges are, and what their mobility is, and the density of mobile charges, that actually all has to do with the particular material. It's different for copper or nichrome or silicon or carbon or whatever. And so if we just rearrange this a little bit, we can write all those things that are related to properties of the material together. We can write So these are properties of the material. And we give this quantity a name. It's called the conductivity. And the symbol we usually use is the Greek lowercase sigma. And so conductivity. So let's calculate a conductivity just to see what it looks like to do this. Maybe we can make it multiple choice. We'll just do it together. The conductivity of copper is, well, we just have to calculate that quantity. So the mobile charges in copper are electrons. So to the minus 19 coulombs times the mobile charge density, which is 8 times 10 to the 28 electrons per cubic meter. Really, electrons isn't exactly a unit. It's mobile charges per cubic meter. So we'll just write and the mobility is 4.5 times 10 to the negative third meters per second per volt per meter. So this is drift speed and this is electric field, right? And so if we multiply this all out, we get 5.76 times 10 to the 7th, I think, yeah. Ampere per square meter per volt per meter. And yes, you could simplify that if you wanted to, but at least here it the units make some sense. Now, since this equation for conventional current has not only the conductivity but the cross-sectional area of the conductor, sometimes this is sometimes people actually rearrange this and write the current per square meter is just equal to the conductivity times the electric field. And that's why we have in the units for conductivity, we have amperes per square meter, and that's referring to the cross section of the conductor. And it even has a symbol. It's called J. We won't really use it very much. It's called the current density. You'll encounter it in more advanced electricity and magnetism courses, but it's not a thing we're going to worry about very much here. Okay, an interesting question that we could ask, we've talked about nichrome, those bare metal wires you find in the electricity kits upstairs, being a much less good conductor than copper. So how much higher is the conductivity of copper than that of nichrome? So we want to calculate, we'd have to calculate the ratio, or so we know, what did we just calculate? We calculated the conductivity of copper. So we could either calculate the conductivity of nichrome, or we could just, right? So what do we get here? We get 8 times 10 to the 28th electrons per cubic meter times 4.5 times 10 to the negative third meters per second per Newton per Coulomb, divided by 9 times 10 to the 28 cubic meter, not very different. But here we have 7 times 10 to the negative fifth meters per second per Newton per Coulomb. So what's that going to come out to, approximately? Well, this is approximately 1. 7 is approximately 6, 10 to the minus 2 over 10 to the minus 5. So around, it must be around 57. So copper's about 57 times greater than a better. That's what you got? Yeah. So conductivity is just a measure of how good a conductor a substance is. It doesn't tell you what a particular piece of that substance is going to do in a circuit, because that depends on the geometry of the substance. It depends on the cross-sectional area of the wire. It depends on the cross-sectional area. It depends on how long it is, right? And so you have any questions about conductivity before we go on? Okay. Really not that much to it. So for convenience, when analyzing particular circuit, yes, Jonathan?
Sorry, but doesn't mobility change with temperature as well?
Mobility does change with temperature. So all of this stuff has to do with circuits where the temperature is fairly constant. I think this stuff is probably defined at room temperature. I mean, we're calculating this at room temperature, right? And in circuits, you've certainly seen that the temperature of the light bulb filament goes up a lot. Circuits we've been using doesn't go up very much. And we'll do some experiments after spring break with things that are actually called resistors, which are little hunks of carbon with stripes painted on them, which is a color code which tells you exactly what's going on with that particular thing. And they don't change. In the circuits we build, they typically don't change temperature very much. So this is indeed a calculation at some temperature. It's probably room temperature. Yes?
And the temperature of a glowing bulb filament is like 5,000 degrees.
Yeah, it's like, yeah, you can of a glowing thing by just comparing it to the color of the sun. The bluer it is, the hotter it is, and so a glowing bulb filament looks roughly like the sun, and its temperature is roughly the temperature of the surface of the sun. So it's high. So for a particular object, like a piece of wire that we're going to put into a circuit, we often lump together the properties of the material and the geometry of the object. So this combines conductivity, which is the properties of the material, plus the geometry of a particular object in a circuit. So let's go back to our equation for conventional current. We have conventional current is the conductivity times the cross-sectional area times the net electric field object. And the net electric field we can actually rewrite because we know that the potential difference is the electric field times the length of the of carbon or whatever our thing in a circuit is. And that electric field, you have to have a constant current through this thing in a steady state. That electric field is uniform throughout this object. We can write potential differences is just E times L, the magnitudes. And so therefore we could write this conventional current is the conductivity times the cross-sectional area times the potential difference across this object, wire, whatever it is, resistor, divided by its length. And if we write it this way, and the reason for writing it this way is, first of all, we tease out another piece of the geometry, and second, this is the thing you can measure with a meter. You've done that. So these two things are geometry. And conventionally what we do is we lump together the conductivity and the geometry, so we can rewrite this as so the conventional current is the conductivity times the cross-sectional area object we're putting in the circuit times the potential difference across this object. And this quantity here is actually defined as 1 over the resistance. So sigma A over L is 1 over R. This is resistance. So clearly resistance is going to be equal to L over the conductivity times the cross-sectional area. And so we can write I is equal to the potential difference across a resistor divided by its resistance. So so let's just record those two things here. So conductivity is charge on the mobile charge density, charge mobility. Resistance is the length of the object divided by the conductivity times the cross-sectional area. And it has units of, this is a quantity that gets used a lot, so it's got its own unit. Obviously, you could come up with units in the fundamental SI units, but it has units of ohms, named for yet another physicist, this one German or Austrian or something. I think his name was Georg Ohm. And since ohm sounds like omega, we use the uppercase Greek omega as a symbol for ohms. I suppose because nobody knew Sanskrit, so they didn't know how to write an ohm, a Sanskrit ohm symbol back then, which would have been even better, but so let's just and so we can, here, let's just, never mind that. Let's just calculate the resistance of a carbon resistor. So you'll see, you may have, in the little bag in those electricity kits, you may have seen some carbon resistors. They look like sort of an oblong blob with some so if this resistor has a length of 5 millimeters and conductivity of carbon is 3 times 10 to the 4th. Ampere per square meter per volt per meter. And let's say the cross-sectional area of this thing is about, if the diameter is 1/10 of a millimeter, that would be 1 times 10 to the minus 4 meters squared times pi. Or let's say it's square. Let's just make it square. So that would be oh, the area in this example actually is not that. The area is 0.1 square millimeters, which actually comes out to 1 times 10 to the minus 7 square meters. And if we multiply that if we assemble that into R's, so resistance would be the length 5 times 10 to the minus 3 meters times 3 times 10 to the 4th ampere per square meter per volt per meter times 1 times 10 to the negative 7 square meters, and we get that all done, and it comes out to something like 1.67 ohms. And you'll find another nice thing about using these sort of conventional units in circuit analysis is that we're working with numbers that are a lot smaller than 10 to the 18th electrons per second, and cross-sectional areas and whatnot. Resistors are typically you know, an ohm to a few hundred ohms that we might be working with. Currents are in the range of a hundredth or of an ampere to a few amperes. You know, so the units just are kind of nice. Okay, so let's just see, so questions about this. And again, yes, because conductivity is in there and it's got mobility in there and it's a function of temperature. But we will assume most of the time that the temperature of this object is constant in our circuits. Not always. In fact, there's even a term for it. If resistance does not change as current increases, we say this resistor is an ohmic resistor, and if it does change, it's not ohmic. And of course, since current increases, the a big potential difference across something. Okay. So let's just do a few simple applications here. I think we're okay. So how do we solve this problem? Okay, so at least one person has an answer. Several people have answers. Lots of people have answers. Cool. All right, so what we're going to do actually is just use our standard tools and write a loop equation for this circuit. Now, there are some standard sort of graphical abbreviations for circuit elements that we can also use to make it much easier to draw a circuit quickly. So I could do this. But I can also use these standard abbreviations. So here are the standard abbreviations we're going to use. Excuse me. Pollen. And a long line is a battery. And by convention, this is the positive end, and that's the negative end. So that symbol. So now I can simplify this drawing already by just drawing two batteries here. A resistor, instead of having to draw a light bulb, we just say we don't care what the resistor is, it's just some resistor, and a battery usually has some lines coming out. A resistor is a zigzag line like that, so I can put a zigzag line like that, and then just show the connecting wires as connecting wires. Typically people draw nice square lines when they're drawing these circuit diagrams. Of course, that has nothing to do with what your circuit really looks like, because you've got wires curving, but this is topologically equivalent. What do you think the symbol for a capacitor would be? Yep. Yeah, it's just going to be two lines of equal length. So we did this analysis, and now we did a round-trip potential difference. So starting, I drew my batteries with the positive end here in this circuit and the negative end in that circuit, but never mind, we'll use this one. So if we go around this way, we have plus 2 EMF minus the potential difference across the bulb is 0, which says that the potential difference across the bulb has to be numerically equal to the EMF of the battery. Again, we're neglecting the small potential difference across the connecting wires because the electric field in the connecting wires is so small that we do. And so we have 3. Well, we can write this in terms of current and resistance, right? Because we saw that current was, for a given circuit element, the potential difference across this thing divided by the resistance, or delta V is current times resistance, if we do a little algebra. In some previous life, you may have seen people write this equation as V equals IR. Don't do that. It's not right. It's not the potential at a point. It's a potential difference. Okay, so we're just not going to do that. So current times resistance equals 0, which means that 3 volts divided by 0.075 amperes was our resistance, which indeed was 40 ohms, right? So you see we're doing exactly the same thing, we're just using different symbols. All right. There's a footnote about ohmic and non-ohmic resistors. For an ohmic resistor, if we plot current versus potential difference, why do you plot it that way? Well, as you increase the potential difference in a circuit by adding batteries or turning up the knob on a power supply or something, the current goes up. If we get a straight line, the straight line, what's the slope of this line? What's the meaning of the slope of this line? It's related to the resistance. Is it the resistance or is it? So we have I is potential difference over the resistance, so it looks like the slope of this line would be 1 over the resistance, right? So if that's a straight line, then the material is ohmic. And if it's not, if the current starts, if the resistance, see the resistance gets bigger if it gets hot, so it should turn over. There's another kind of interesting material where this plot looks like this. And the interesting thing about the plot is it goes along at 0 for a while, and then it actually increases rapidly. This is how semiconductors work, and semiconductors are important because the computers in your laptop and your phone and your car key and everything else are made from semiconductors like silicon. And what's actually happening here is that what changes as you get a high enough potential difference is actually the density of mobile charges. So what happens is as you apply a bigger and bigger electric field to the material, it affects the energy of charges inside the material, and eventually you generate some mobile charges where there weren't any before. Now often when you talk about semiconductors, you talk about the mobile charges not being electrons but being holes. What's a hole? A hole is a place where there isn't an electron, so it's a localized deficiency of electrons. They're called holes, and they end up mathematically acting like a positive charge with the mass of an electron. So in a semiconductor, the carriers in this sort of more abstract sense really can be positive. Okay. So questions about, yes?
I have a question. So like the holes you're talking about, are they similar to like electron doping?
Well, the way you don't dope a semiconductor with electrons. So to make a semiconductor do a better job of producing mobile charges at the potential difference you want it to, you often don't use a pure semiconductor. So silicon, for example, can have some other elements diffused into it. And some of them are things that like to give up electrons, and some of them are things that like to accept electrons. And so they're called p-type and n-type materials. And so that's, when they talk about doping a semiconductor, they mean adding some other elements, so that your chip isn't made of pure silicon, but it's got germanium or arsenic or something like that, a little bit diffused in. Okay, so what can we do with this? Well, we can do what we've been doing. So let's do something a little bit general first, and then we can do something more concrete with it. So here's a circuit that has 3 resistors, resistor 1, resistor 2, and resistor 3. And suppose that we know the resistance of each of these resistors, and we know the EMF of the battery or the power supply. How do we find the current in the circuit? Well, we can write a loop equation. So we have EMF minus the potential difference over resistor 1 would be the current through resistor 1 times its resistance. And the potential difference across resistor 2 would be the current through resistor 2 times its resistance. And likewise for resistor 3. And that's a problem because it looks like one equation with 3 unknowns, but we can save ourselves with node equations, right? Because if we put a node here, what do we know about the current coming out of R1 and the current going into R2 in this circuit? They have to be the same, don't they? So I1 has to equal I2, and likewise, if we consider this node, I2 equals I3, so they're all the same. So this reduces to EMF minus IR1 minus IR2 minus IR3, or doing some algebra, we can just, so then we can get the current by simply dividing this by the sum of all the resistances. So this behaves the same way as if you had one big resistor in it whose resistance was the sum of these. And this is a series circuit, right? On the other hand, what would happen if we took those same resistors but we arranged them in parallel? So now we have R1, R2, and R3. Well, we have three loop equations. We have EMF minus I1 R1 equals 0. EMF minus I2 R2 equals 0. EMF minus I3 R3 equals 0. And if we want to know the current produced by the battery, of course that's going to be the sum. We'll just call that I0, I guess. We'll call it, say, I0 is I1 plus I2 plus I3. Now, is it the case that I1 and I2 and I3 have to be equal in this circuit? No. The only time they're going to be equal is if the resistors are the same resistance, right? So, however, we can do something sort of interesting here. So it looks like the current through resistor 1 is exactly the same as it would have been if the only thing in the circuit, because it has the full potential difference of the battery across it, as witnessed by our loop equation, again neglecting the connecting wires. And likewise, the current R2 is the same as it would have been. So we can actually write our node equation a little differently. We can write it as EMF over R1, solving for this equation for I1 and plugging it in there, plus EMF over R2 plus EMF over R3. And so the current coming into the current here, coming into here, is equal to the EMF 1 over R1 plus 1 over R2 plus 1 over R3. And so sometimes people say that this is like making these three resistors equivalent to another resistor, but the equivalence relation is different. It's not just a simple sum. So in this case, it would be 1 over the equivalent resistance would be 1 over R1 plus 1 over R2 plus 1. And we're just doing math here. I mean, equivalent resistance means mathematically equivalent, right? Now, there are lots of ways to screw up applying this. You can failed to do the algebra correctly when adding inverses. You can try to apply it to more than one group of resistors in parallel, but it is useful. It saves. You don't have to do that. You could solve this from loop and node. It saves time sometimes in analyses. Okay. So we'll do it. We'll analyze it. Yes.
It might be useful to notice that since the resistance is the length divided by sigma A, longer length, more resistance. That makes sense, right? And it's divided by the cross-sectional area. And I use a wider wire, also less resistance. So it kind of makes sense.
Yeah. Yeah.
Longer, thicker, it's going to work like that.
I bet they invented it because they weren't actually thinking microscopically or geometrically at all. They just wanted to know what happens when I put this thing in a circuit. But okay, there's one more actual concept before we analysis. And that has to do with power. Now we know that circuits don't run without some sort of power supply, a battery or something. And energy, a battery or a power supply puts energy into a circuit, and then that energy gets dissipated in the circuit. You may see as heat and light from a light bulb, or maybe it's just heating things, or maybe it's turning a motor or whatever, but it's doing something. And power, of course, is energy over time. And in this case, our concept of potential energy, electric potential energy, is useful here because remember that was Q delta V. So for a single charge, the change in potential energy for a system was the charge multiplied by the potential difference through which it traveled. For a current, we typically write that the potential energy change for a system is equal to the amount of charge so in coulombs that travel across a potential difference. And so if we divide this by time, this happens in a unit time, so it would be the amount of charge per unit time, say, entering this resistor would tell you about traveling through that potential difference would be related to power. And in fact, this quantity is just current. It's coulombs per second. So a very general relation is for any circuit element, the power output of the battery, say, is the current coming out of the battery times the potential difference across the battery. The power dissipated in a resistor is the current going through the resistor times the potential difference across the resistor. So for any circuit element, power is just current. Okay. So quickly, we have time to do this? Sure. Okay. So let's consider a a couple of different circuits. Let's consider a circuit with a 3-volt battery and a 30-ohm resistor. So what's the current in this circuit? The current through this resistor. We have a loop equation, right? So what do we get for the current here? Just going to be the potential difference across the resistor, which is the same as the potential difference across the battery. So we have 3 volts over, which gives us 1/10 of an ampere, right? Okay, let's try a different resistor in the same battery. We still have 3 volts. But now we've got a 5-ohm resistor. So the current is, again, going to be 3 volts over 5 ohms, which gives us 0.6 amperes. So we see again that it's not just the battery that determines the current. It's what's in the circuit with the battery. Okay, so let's put these resistors together into a circuit. So here's 3 volts. Here's our 30-ohm resistor, our 5-ohm resistor. What's the current in this circuit? So is it 1/10 of an ampere? Or is it something else? So is it going to be the same as, I mean, we have this big resistor here, so that it's, we have the small resistor here. Well, so we have our loop equation, EMF minus, well, we know that I1 equals I2 here, so we'll just go I times R1 minus I times R2 is 0. Current is 3 volts over 30 ohms plus 5 ohms. And that's going to give us something a little bit less than 1/10 of an ohm, isn't it? Okay. So we get, did anybody actually do this? It's going to be a little bit less than it, so it's going to be like 0.086 amperes. Sorry, ampere. Okay, so the total resistance in the circuit went up and the current went down. So what's the potential difference across this resistor? How would we calculate that? Okay, so it's the current times the resistance, so the absolute value here. So that's 0.086 amps times 30 ohms. If it was 0.1, it would be 3 volts, but it's a little bit less than 3 volts. So it's yeah, I think that's what I got to, 2.57 volts. potential difference across this resistor is the current times that resistance, which would be 0.086 amps times 5 ohms, which had better come out to what? Better come out to 0.43 volts, because this has to, I think it does. So suppose we tried to make a graph of potential around a circuit. So this is just location in the circuit. So we'll say this is location A, B, C, D, E, F. So here's our locations. A, B, C, D, E, F. Okay, so we're starting, so this is potential and this is location. And let's define for our purposes, we're going to say that even though we really only know a potential difference across the battery, we'll say that 0 here comes, so the negative end of the battery is 0. So if we're at the positive end, we're 3 volts up from that. So we're starting here. So how much does the potential change as we go along the wire from A to B? It's a really tiny change, isn't it? So this wire would have, this graph would have maybe a tiny negative slope, but not very much. Now from B to C, we have kind of a big change in potential, right? And since we're going around this way, this was positive, so that must be negative. So it must drop by something like a little more than 2.5 volts. And now, if we go along the wire from C to D, not much happens. And then from D to E, that's the next resistor, and that should be 0.4 volts. And then we go back to F, and then to get back to A, there has to be a big potential increase across the battery. So our round trip potential difference we can kind of map it as we take the trip. Okay, we have time for one last thing here, which is what happens if instead of the series circuit, we put these resistors in parallel. So this one, and that's R2. So what's the total current? What's the total current through this circuit now? Current coming out of the battery here. So notice that our loop equations look like this. We have EMF minus I1 R1 equals 0. And that's exactly what we saw over here, right? So it looks like I1 is going to be the 1/10 of an amp because the entire potential difference of the battery is across it. So this part of the circuit behaves as if this resistor was the only thing in the circuit. What's for the other resistor? We have EMF minus I2R2 is 0. We already solved that problem, so it looks like I2 is 0.6 of an amp. So what's I0 here? 0.7 of an amp. So when we put the resistors in the series, the current went down to 0.086 amps. When we put them in parallel, the current is actually the sum of what it would have been had they been by themselves. It went up to 0.7 amps. This is a little bit like increasing the cross-sectional area of a resistor by putting two in parallel, and this is like putting them in series is like making them longer by stringing them. So again, we see the battery isn't always producing the same current. It depends on what we've got connected to the circuit. In which situation is the battery putting out more power? In the parallel circuit or in the series circuit? So remember, the power output of the battery was power is current times potential difference. So in the series circuit, we have 0.086 amps times 3 volts. In the parallel circuit, we have 7 amps, 0.7 amps times 3 volts. So the power output of the battery is just a lot higher. It's generating more current in this circuit than it is in that circuit. Questions? All right, we do have a quiz. You do need an abacus or something. This is intended to be an extremely straightforward quiz, so don't overthink it.